I mean, he does that at the end of the semester with the survey. If you don't show up for the survey, he takes an actual attendance of that day, and then when he leaves, and then he says whoever doesn't show up can't get the study guide for the final. So that's like the one day you actually absolutely need to show up to the class.
Then you have Yankee who like tells you can turn the homework 2 months late.
Right. But then he also promises he's going to fail you, so that you have to retake the class, and then he's going to fail you again.
Gain's very lenient on homework. As long as it's in before the test, it's pretty good.
Yeah.
Huh?
Yeah, we're talking about
please.
Gain in 2 years.
I'm not sure if I will be able to attend Braden's presentation tonight because of the chemistry seminar. It is a little earlier, but
Oh, that's today, isn't it?
When's it?
One of the candidates for the new professorship.
yes.
So I don't have anybody from that club, so I can't make it.
I was gonna skip math club anyway.
I might have to skip because I have a test tonight at the same time as the class. So. You picked the worst day possible, it looks like.
Who we are and what are we doing? I wipe off all memories each night and need to recall in the morning. It looks like we are in class. Computational chemistry. And we are done with first chapter and starting the second one. Okay. We always want to do presentations. Please sign up for one. Okay, now I have a catch. So, if you have some higher priorities, like reading fun novel or doing other homework, and you do not want to listen and record what I'm doing, today is the best time. Today is a less useful, means useful, less lecture. And when I do not know, you will see. I don't know why do I put it. It was too late to skip it, but it was probably the bad idea. The original idea of the thing that I will show today was to make you more comfortable and less scared about spin, like electron spin up and spin down. But when I looked on it with a sober eye, I thought this lecture will scare everyone to the death away from spins. So whether you recall a single word from this lecture or not, it will not affect your progress in the course. So it's only for your curiosity. Do not record, do not listen, do not look here. A little bit more serious on, let me scroll through and I build. You know, we are in the course, we need observables. Last time we are dealing with electronic degrees of freedom and we do want to solve for many electron wave functions, and we know that there are several steps that bring us there. One of these critically important steps is so-called Slater determinant, which concept of determinant was presented to us by Alisa, right? And concept of Slater was shown to us by Daniel, right? So you build a matrix and wave. It is a way how the multi-electron wave function constructed of single electron wave functions or orbitals, if you know them. We are going to go this way, and we will reach the level when we can write a program, a code for Hartree-Fock. We are not going to do it. We are not programmers. It's not our goal. But each of us should be able to supervise a professional programmer and tell how to write such program. To supervise is easier than to do things. you may develop this idea. What is this? I was recalling to someone what is non-adiabatic coupling, but you know this, right? How it's from previous chapters. Nuclear, electronic summation, but if this part response of electronic part to nuclear elongation is 0, then it is just product. You all knew this. Good. Next. It looks very similar to your homework. Maybe it is from one of the previous years, but let me bring it up. I looked through your models, and you did something like titanium, 2 OH groups, and then O, titanium, O, titanium, H, right? Something like this. The idea is to do a sequence, a progression of those. So with only 1 titanium, with 2 titanium, 3 titanium, 4 titanium, 5 titanium, and then do apply all your skills toward them and see what happens. So your skills include, we're not going to deal with geometry. Whatever geometry you have prepared for yourself in the previous homework, it is you help or like do otherwise to yourself. Right now, just do single point and find total energy, and orbitals energy, or highest occupied, highest unoccupied, and the gap, and then report it 5 times. Right? So it's not very complicated. And if you think it is too easy, just a little cherry on a cake to do density of states for each other, which you can do, right? I think it will be sufficient. For the, if you really want an extra credit, well, credit is not a problem here in this course, but if you want to excite yourself and you have energy that you do not know where to apply, you can take your extra credit models from your previous homework and do Hartree-Fock single point for them and do the same things for those. Later on, especially if you were victorious in building a true nanorod of perovskite. There is one person who was able to do it. And if you see the very, very last line, there is super extra credit. I didn't mark it this way, but if you take a cluster of this perovskite model and replace one lead with one manganese, and do again the single point Hartree-Fock, there will be surprise, either computational or intellectual, and you may observe. And actually, this surprise is my little excuse and justification for doing today's useless lecture on spins. I didn't start the lecture yet, so it is a little repetition of what we were doing in the lab. So if you have the .out file as a result of Gaussian, you can open it in Gauss view and see a list of whatever you did, and then extract the total energy. Right? And of course, if I'm not asking you to do it, it's not part of homework, but if you ever need it for your research, you can measure all distances and see how these interatomic distances respond to electronic configuration, right? For different electronic states, the distances can be different, right? So Austin and Christian are aware of this very much. No, I do not think I'm going to give this homework. It will be torture for you and me. So it is where we are now. We are done with first chapter. We are doing the second one, and I'm modifying. I'm sticking here between Slater, determinant, and philosophy of Hartree-Fock the couple of meetings on spins that I'm going to justify. One can be happy and survive without spins. One can complete this course without spins, and one can do successful research without spins, especially if you do hydrocarbons, closed shells, no metals. Everything is fine. But if you are lucky to be a part of research group that deals with inorganic, meta-organic complexes, like Christian, you may face the following type of system. A metal surrounded by organic stuff. It's a forgivable word for a person with physics degree. So, and if you look through periodic table, you see that the elements are numbered subsequently, and some numbers are even, some numbers are odd. Great discovery. And if you look on the metal ions, even if they are ionized, some ions have even number of electrons, some ions have odd number of electrons. So sometimes spins are not paired, and sometimes they are very non-paired. Like there are several unpaired spins. And for such situations, we need to have a little flavor, general idea what they are and what to do with them. Later on in the course, we will play with some methods and tools that explicitly deal with this spin degree of freedom. So it's motivation 1. Motivation 2, if you, well, last time I was taking chemistry in high school, last thing that I remember that there are hydrogen orbitals that are specified by 4 quantum numbers: principal, orbital, magnetic, and spin. Last lecture we talked about 3, but spin was forgotten. So it just, one day we need to accept that it does exist. So it was motivation number 2. Motivation number 3. The functional form of slated determinant was offered to you just as stuff to memorize. Where it comes from. Through manipulations with spins and several spins together, wave functions, spin wave functions for like two spins per cup, the shapes, functional shapes of these products, antisymmetric products, come up natural. So it adds a little logic. Motivation number 3. I'm trying to motivate useless activity to have it a little bit useful. And motivation number 4, spins, although they are very offending to those who start looking at quantum theory from the first point, they are counterintuitive. But when you deal with them and when you look objectively, they are simplest possible quantum objects mathematically. And if we need to, and we do need to deal with multi-particle effects, everything we do is multi-particle, so many degrees of freedom, not only like 3 independent coordinates or 3 independent angles of rotation, it is different particles. And the simplest example where multi-particle nature is reflected is set of several spins. So justification number 4. All above doesn't justify sufficiently to do. So it is kind of entertainment. If you were planning, if you were doing lecture notes, now you are released from this duty. Not forever, but for this useless meeting. So, and before we go to actual stuff, here's the thing that you have filled. Some of the aspects will be heavily covered in the lab and homeworks. Some will be for brave people to cover in their personal preparation. The date for presentation, I have a chance to correct it. So first is month, second is date, right? So month will be number 3. March 1st. March 1st. And you know that 3rd week of February many of participants of this class will be not in this city on both sides of trench. I will try to go online and mumble something in the same day and time, like 11 a.m. Tuesday and Thursday. But if you want to listen, you do not need to come into the classroom. You can try to go online to the link. You know the link for the class, right? If you don't, I can distribute it again. So everything what we are doing is not only recorded; it is also broadcast. So you can instead of coming here, you can sit on a sofa with popcorn and just look. So yes, and then whoever is not here today, oh, just one.
It's pretty full.
We'll select most challenging thing to Russell. Since he's not here, probably he wanted to take it. And boxes didn't mean that it is one question. You can sign with one and do not sign for another. I just boxed it because I wanted to present it yesterday in the lab.
Oh.
So the rest is boring, and this is most interesting thing. Let's focus. It will be here. If you before leaving, you can add your wishes. Okay. A little bit more motivation of why we usually talk about spins. So here is the plan, line of narration for Hartree-Fock theory. You already know what is it and how it works. You already get like positive benefits. You take atomic models, you find total energy, you find orbitals, and you analyze. One of the questions in the homework is explained by your own words. What is the mean benefits, significance of energies of HOMO and LUMO, right? And you can tell that by Koopman's theorem, it is ionization energy and electron affinity. And the difference is related to excitation energy. Right? And good. And we'll go over the details of this approximation later in the class, but you have an idea that ionization, affinity, electrochemistry, STM, so we are doing something useful. If you are physics person, you may not like electrochemistry, but you have to like STM. It's not chemical technique, it's surface science and mostly physics. So, Slater determinant, near mean field, which means field created by all electrons to the one probe test electron that we put in or out. And then the Coulomb interaction between our favorite electron and disfavored electron in the sense of Hartree-Fock theory can have two implementations, two shapes: actual Coulomb and exchange. I'm not going to tell what is it, otherwise I will have nothing to do next week. But there is a part shape, angle on Coulomb interaction that looks very different, and it is taken into account in this article. And then there is a protocol how to combine all the things and do it, obtain the result of this Hartree-Fock theory, which is total energy and set of orbitals, in a self-consistent manner. So those problems that cannot be diagonalized directly are solved by self-consistency. It's a standard thing, and you may have seen it before, right? Did you? No? You didn't solve self-consistent with like physics research? Electrostatics, electrodynamics. Did you solve numerically Laplace equation? Did you took electrodynamics?
Yeah.
Yeah.
We did everything by
Did you
hand.
have
Like,
computer lab for electrodynamics?
no.
No, it was all by
No.
hand.
You should, okay.
Packets of homework.
That's
But
We're open till 5 a.m.
Yeah.
Please look forward for idea and practice of self-consistency. Right now it's just two words, but later you'll see meaning under it, and it is one of the breakthrough of humankind. Very simple idea that allows to solve unsolvable. Okay, so it is what we do, right? Equation of electronic part, we know slated determinant, and you, if I will be recording it, I will mute microphone right now. Not for general. Electrons rotate around themselves. Well, you cannot tell it in public. It is not a justified hypothesis or discovery, but if they would rotate around themselves, they would have a quantum number associated with amount of rotation, angular momentum of rotation, one or other side. See, this globe is different direction. And this is actually what is spin.
It's blasphemy.
Yes. So, if you disagree or agree or just aware of this discussion, you already know what is spin and why it is needed or not needed. And it is just force index for atomic wave function. Good. What else can we tell about spin? If you were practicing physical chemistry 1, it is not possible to scare you. You saw most of it. But if something is too unpleasant or challenging, just close eyes and wait. So, mathematically, up and down, right? So just two states. Simple. So two basis states, and any spin state is a superposition of these two things.
This looks like a feedback loop of laughter.
A little bit.
I didn't
You're
expect
specific.
that this meeting will be so fun.
See, in chemistry, we just like accept it.
It's wrong.
So different groups of people have different abbreviations, like alpha and beta, up and down, 0 and 1, plus or minus. That doesn't matter, but just there are two of those. And if you look only on spins, only on these things, and you know everything you do is based on quantum theory, and in quantum theory you do have operators, so the stuff that changes wave function. So if you have like spin up and you want to do spin down, you apply what? Annihilation operator, right? You can call it S minus because it just flips to, and you can or up that goes from another side, and you can formulate it as a ket times bra, right? Like if you have wave functions, they are either bra or ket. If you have a scalar product or expectation value, it is bra times ket. And if you want operator, you do ket times bra. Right? So when these two angles sneeze their noses, it means operator. So spins, quantum operators, hoppa. So we change one basis function into another one. So it's quantum operator. So this is ket of owl, this is ket of skylark, this is quantum operator. Good? I told you it will be useless lecture. And last year, one of the students came complaining about this lecture to the advisor. telling like, I came to study computational chemistry, and there were birds.
Okay.
Okay, I like birds.
Bird goes tweet tweet.
So, when there are bra and cat together, they give a number. If they are the same, it will be number 1. You know what bra and cat means? It's if you write the word bracket, you just split them on two parts.
This is like a physics inside joke day.
Well, same. If it is the same on the left and right, it will be 1. And if it is different, it will be 0. Okay? So now you are certified experts in direct notation.
Landon, how does that make you feel? Full semester just down the drain in like 10 minutes.
Yeah, I took the one where we actually derive quantum mechanics too. So.
Yes.
I like it, yeah.
And this one is operator, projector operator. So it converts an owl to an owl. Means identity. Doesn't change at all. And this one converts owl into skylark. So it is a conversion operator, like creation or annihilation operator that does something finally. So this wizard, it means that the cat times bra applying to cat makes another cat, because these two convolute into one and you obtain this one, right? So you redefine this one. Instead of operator and wave function, you redefine this as scalar product times wave function. Good. Same thing. If you apply creation and operator to spin down, you are getting this beta. You just flip spin up. Right? So here is your owl. Here is your wizard. Here is your skylark. You may have noticed the comma 1, right? Because, and it is something novel compared to, well, I'm too early, but comma 1, because there are 2 spins. So later we will look onto more than 1 spin. Just even if you do not do any derivations, if you do not do any homeworks, just we need to understand that this creation and annihilation spins, there are more than 1, always in the nature. We have a universe with more than 1 electron, more than 1 spin. And when they are considered together, we need wave function of that consists of bases like all up, all down, part up, part down, and we need to feel fluent about this aspect. Well, nothing new here. You already saw it. So if you try to apply lowering operator to spin down, you'll get 0, nothing, because of this orthogonality. So in some operators you just get nothing. And this is algebra of operators that is used later for some helpful derivations. Again, keep not listening, keep not writing. There will be nothing useful for the course. It's just aspect that help you to view from right side on things we will be doing later. So no practical tools, no practical protocols. Again, same thing. I'm not telling anything new. If you have a spin wave function, it is composed with, of up and down with some amplitude of probability. So it can be 50% up, 50% down. This is completely normal in quantum theory. For human thinking, it is very abnormal. Therefore, some people hate quantum theory. And if you want something that humans may like, you need a probability. How probable is that the system has a spin projection up? Then you take conjugate value, a star, with this one, and this is probability. So in the simplest case, those things are like square root 1 divided by square root of 2. And if you take this one, there will be probability 1/2. 50% here, 50% there. But do not develop, if you hear it once in one course, you may develop an idea that probability is always 50%. No, it can be anything. Well, do not listen. I'm just mumbling for myself. What happens if you place together two projectors, two lowering operator and raising operator? So one that converts from up to down, and second that converts from down to up. The middle part can be set to 1, and then it will be projecting from up to up. So it will be projecting from, let's see, one excited state. Well, we do not have excitation if there is no magnetic field. The spins have the same energy, but we're just projecting from one spin to another. Later on, thinking in this way, procedures like this, of putting together two operators, can be useful and helpful in formulating Hamiltonian of the problem, which is often needed. In general, but not needed in this course. Do not listen, that's in trouble. Let's go for it. So, where will I stop? Will I continue this entertainment or challenge or unpleasant things forever? I would stop, and I would be happy if I can get from this discussion the form for Slater determinant. So if on this language I do formulate system of two spins 1/2, formulate the total spin squared operator and diagonalize it and get a functional shape similar to Slater determinant. If I do it, I will be happy and I will stop. If it will be too late, I will stop anyway. So when we have the general formulation of spin wave function, and whether sigma is frequent when we speak about spins, we can also, this superposition wave function can be ket and can be bra. And when we do have an operator, we can also find its expectation value or its matrix elements. It is a standard procedure that people entertain in quantum theory. So the operators are useful to represent in matrix form. And one can guess and get the answer how an operator look in matrix form immediately. If you, but if it is a little discomfort, there is a little boring way how to identify matrix form for each of those operators. So if we do have this general form of speed wave function in form of cat, in form of bra, and one of the operators in between, we can open this line in a careful way, which I don't want to do right now. It's a good idea for CHEM1 next year, if you take. And then there could be, come on, E1 completed. Yes. So if one goes onto this road, one can convert each operator into form of a matrix. So the matrix for raising operator will be one element equals one, others are zero. The states, superpositional state of one spin, are just vectors with two components, right? Which can be either row or column. And if one apply such matrix to such column, it will flip everything that was here into there, and it will just remove anything that was here. Same way one can formulate the annihilation operator, having one at a different spot. And if one multiply these two matrices together, it will be one in this spot, and all others will be zeros. So anything we talk about spin can be formulated in a matrix form. Why? And what is the next step? There is a way to repeat the same procedure in the basis when we have two spin wave functions. So C alpha 1, C So if we speak in the language of two electron wave function, right, then the state of such wave function is, if you perform multiplication of these two things, C alpha 1, C 2, alpha 1, 2, is C beta 1, C 2. Of 1 C beta 2 alpha 4. How would you have this? And C beta 1 C beta 2 beta 1 beta 2, which means that there are amplitudes of probability that both spins are up, both spins are down, and then one up, another down, one down, another up. And in order to specify two spin wave function, one needs 4 expansion coefficients, which related to one electronic one spin coefficients, but we will consider, well, we will not consider anything, but one can consider those things as 4 coefficients, maybe like C C1, C2, C3, C4. So C independent coefficients. And the spin wave functions, if you do not have external magnetic field, if you do not have, if like Hamiltonian is nothing, zero energy, but they still, the spin operators needs to be eigenstates of the total spin squared operator. And only those values of this C coefficient that will match the this equation, so eigen, which will be eigenvalues, here is the S capital squared. Will be allowed to exist, to survive, while others will be like disallowed to exist. And with this background, we will do nothing. But we could formulate this equation in terms of this matrix operators, and then find the allowed values of this C1, C2, C3, C4 coefficients. Make sense? Generally. And then one of the solutions, okay, I'll put it here, will be that C it resists. One of the solutions will be that pen. Okay, good. One of the solutions will be that C1 equals C4 equals 0, C2 equals 1 over square root of 2, C3 equals minus 1 over square root of 2. This would correspond to a singlet solution, so that there is no chance for both spins up, there is no chance for both spins down. There are only chances that one is up, another is down, or opposite, with minus sign in between. If we meet again in one of the other courses, I will go into details of this, but not now. This is not the goal of this course, and we already spent too much time on this. So I believe that it will be a good idea, unless it is too early. No, it is not. So you will not mind if we stop now? Okay. So I hope this you didn't suffer much of this useless lecture. And what do we take home? Slater determinant form is justified, even if you didn't sacrifice enough time into this. Spins exist. And later on, there will be very immediate practical consequence. We will do so-called unrestricted Hartree-Fock and general unrestricted electronic structure, where there will be two sets of orbitals. One orbital with explicit value of spin up, another set of orbitals with explicit values of spin down. This is not needed if you do closed shell hydrocarbons when spins appear. But if you go into transition metal organometallic complexes, it is very needed. Or if you have magnetic doping into your quantum dot, it is also very needed. And if you, in your homework you try to do the last super extra credit, you will realize that either you gain an error, or you and Gaussian will try to catch this error before you start and specify spin multiplicity and unrestricted type of calculation, or you yourself will realize that you need to correct it. Enough. We didn't progress too much towards Hartree-Fock theory, but after this, when next lectures will be more useful, you enjoy them more.